I do actually do this as a half-day course for ASHRAE, so it's quite a lot of material. But tonight I'm going to present this in about 30 to 40 minutes and leave time at the end for some questions. So it's really just a brief run-through. I was in fact in Calgary in November at the Cold Climate Conference. I was tuned up for cold climate, so the cold in the north here isn't too bad, but it's quite interesting at that conference to find that we are looking as an industry to develop net zero energy buildings in cold climates as well as hot and temperate climates, so it's quite a challenge. As you can see here, I'm with Low Carbon Design Consultants, which is a new teaching practice we set up in Liverpool to work on low and zero carbon designs and to bring new people into the industry, training with the University Technical College that they've got there on how we can achieve these kind of objectives. Now, of course, just a brief introduction as to why we're trying to do this. I think we all know that CO2 levels in the world are rising due to the activity of mankind, use of fossil fuels and so on, and that's causing the planet to warm, and it's having some adverse impacts. So the use of fossil fuels is giving us problems. So we're also using them up fairly rapidly as well, so we're running out. So our precious resource there is going to disappear within a certain length of time. And whilst we use these up, there is this kind of flywheel effect that CO2, which is being produced, is still being absorbed into the sea and the air and into the earth, but it is there, and it will come back, if you like, to haunt us, and sea levels may rise as a result. So we see these kind of pictures here, which are a bit dramatic, and it's interesting when I do this talk in the States and we show this sort of illustration here, which indicates the kind of sea levels that might have an impact on North American cities. And I was quite surprised, for example, to find that Tampa would be half flooded if sea levels rise only 1.5 meters, which is certainly within the sort of forecasts for the next 1 to 200 years if we continue to produce carbon at the rate we're doing. It's interesting, that slide there, to see New York there as well, actually, and that won't flood until we get 3 to 5 meters sea level, but in fact it did flood last month, as you know, with Hurricane Sandy getting there. So they've had a bit of a taste of that, and I guess as a result we'll be making increased risks to reduce carbon in order to protect their cities on the coast. You see Miami down there in the bottom right-hand corner. A mere 1 meter rise would flood most of Miami and in fact half of Florida. So it's serious stuff really, and we do need to do something about it. In the meantime, of course, predictions are that we will continue to want to use energy in one form or another, and if we continue to use fossil fuels and increase at the rate, then clearly we're on a path to all sorts of problems around the world. Now, why are buildings important in this? Well, you can see from this slide that buildings are responsible for a major chunk of the amount of carbon we produce. These slides here are based on UK buildings, and it's taken from information from DEC and DEFRA, but the diagrams are similar in the States and other developed countries. Buildings being responsible for approximately half of the carbon that we produce, and then industry and transport, which again is related to where we put buildings and what they do, responsible for the rest. And then we can break that down, as you can see there, to see just how carbon is being used around the UK and the world. And we do have quite a lot of information actually when we dig down into where that carbon comes from in different sectors. You can see that top right hand diagram. In the domestic area we have about 7% of the energy consumed is to do with space heating. Water heating is another 25%. And then cooking is only 5%, and lighting, appliances, TVs and whatnot, only 13%. So in the UK, heating is still by far the biggest energy consumer that we have, and it's an area we really have to tackle. And you can see the other areas we've got there in transport process, space heating, these sort of figures. I've just returned from an EU workshop in Brussels where there was an interesting piece of research going on called the Carbones scheme, and it's a method of looking at the amount of carbon in the world. This is still at research stage. It does give us a chance here to look at the amount of carbon in terms of fluxes and pools and carbon stores across the globe. Some of those are based on space, where they are, in the earth, the water and the air, forests and whatnot. And then they're of a temporal nature. Sometimes they exist, as you say, in a forest, but then that forest might get cut down and burnt, in which case the carbon ends up in the atmosphere. So this research is really bringing that together so we can see across the whole world how much carbon we have, how much we're increasing by, how much is in store and how much is being emitted. And it's called the Carbonid scheme, and that, as I say, is still actually at research stage, but it's an interesting big overview of the whole thing, looking at all countries. Coming back to the energy utilisation, you see the business as usual situation is quite concerning. That picture in the state of the plants in the States show that we're looking at very high electricity consumption. 72% would go to buildings, and that's of all carbon emissions in America, so it's a fairly big figure. And of course the other thing is the projection of how that's going to increase over time. Energy has increased, as you can see there, and it's projected to carry on doing so for the rest of this century. So human population is expanding pretty rapidly. People are moving into buildings and cities and looking to use energy in the way they lead their lives, and so we are having to deal with increased use of energy. And that's really what brings us back to net zero energy buildings. If we're going to have to use energy, we're going to have to conserve fossil fuels, one area we really need to tackle are buildings, and we have to try and design these and use these to use as little energy as possible, and ideally to be net zero energy. But the question is, what does that really mean in practice? And I think we have to think about how we define net zero energy building. You can see we can look at labelling systems or fuel statistics or whatever. And in fact, there's different definitions out there. One is the net zero site energy building, which produces as much energy at the site level as it consumes. We can look at source energy, and that would be how much energy on an annual basis is used at the building compared to how much it actually requires at the source, at the power station or power plant or the gas field, wherever that energy is coming from. We could look at net zero energy cost, so that's not really the amount, it's how much we're spending for energy, or whether we could produce enough renewable energy and sell that so that the amount we paid across a year is zero. The amount we buy in is less than the amount we sell out, so that would be zero cost. And then, of course, if we think of energy in terms of carbon, if that's the big issue, net zero energy emissions for the building. So if we're bringing in fossil fuel energy and we're able to export renewable energy, then over the period of the year we might be able to demonstrate that we actually had a zero emission carbon building. So that's another definition. So looking at net zero energy, is it clear we have to look at the site level, and we also have to look at how energy is produced away from the site and brought into the site. And we need to think about the benefits of doing this. I mean, clearly, if we can get to net zero energy building designed and constructed, we're going to reduce the energy consumption, so that will be reducing bills. We're going to reduce the carbon emissions, which I said before is very important. We'll reduce carbon footprint, so our corporate social responsibility is good. And we will be able to operate at lower costs and conserve resources for longer. We should be able to increase productivity because we're really making cash available to use in other directions instead of spending it on high fuel bills. And we should have a more reliable building because we're less dependent on the energy coming in to actually run the building. We've got a building that is more reliable by perhaps natural energy resources. The design approach which I advocate and which we cover on the ASHRAE course I mentioned is to look at 3 levels, being lean, be clean and be green. And these are really taken from the London Plan, which which talks about dealing with net zero energy design at a building fabric level, a building systems engineering level, and then finally looking at the renewable energy systems we will have to put onto a building to make up for whatever small amount of energy we do use. So moving towards looking at the building itself, we have to try and understand what kind of design standards we are going to use. And it's clear that a lot of the buildings that we do have constructed already are very fine buildings. They're used very effectively and efficiently, and they're going to continue to be used. We can't really get rid of those buildings. The impact of demolishing a building and building the same building in that spot on a zero energy basis would be that we'd have 12 to 13 years embedded energy, or embedded carbon. So that's really not the option. The option must be that we go back to existing buildings and take measures on board that will reduce their energy use to zero or near zero. When we think about the modern buildings that we might construct to be zero energy, we look more like those at the bottom of the slide there, built in the countryside with solar gains onto thermal panels, PV panels and the like, and perhaps using natural resources like water for heating and cooling through heat pumps, some greenery, green roofs, that sort of thing. So we've got that double-pronged attack, is how do we deal with our existing buildings to get energy down and drive those to net zero energy, and how do we build new buildings using new techniques that are zero energy from start. And the design standards that we might use come from a number of different sources. We've certainly got some good ASHRAE and CIBSE guidance, architects are publishing good information, and then we have initiatives like the Bill Clinton Climate Change Initiative, and of course the EU directive, which affects all buildings, all countries across Europe, is looking for us to produce guidance and regulations that will drive down energy use and carbon emissions. Here in the UK, we have our Part L building regulations, and by 2016, they're looking for all new domestic buildings and government buildings to be net zero energy, and by 2019, effectively every building that gets built must be zero energy. So they're fairly onerous targets, and we're looking at how to do that. And at the same time, we've introduced the energy performance rating system in the UK. This is the ASHRAE system in the States. Looks fairly similar, the same kind of approach by looking at that grading, and the Americans really looking to follow Europe there and driving down their energy use and carbon emissions by rating the building at design stage, which is what they're calling the building energy quotient, and then the operational stage, which is the building energy rating. That's what it actually uses. And of course, ASHRAE has produced this vision document, and the board of directors of ASHRAE have set this target by 2030. There will be design tools available which will enable the industry to produce net zero energy buildings anywhere in the world. So how do we go about designing it? What sort of design standards are we going to use, and what's the methods we are going to take on board? And I think the first thing is we really have to do a lot more energy modelling, building modelling. We need to understand how the form of the building, its orientation, how many windows, where those windows might be, what type of windows, single, double, treble glazed, what kind of shading. And by using the modern design tools that we have at our disposal, we can understand in a lot more detail how buildings function throughout the whole year. We're looking at lighting that might come in, use natural light more than artificial light, looking at window frames, and looking at where we might have insulation and thermal mass in the building. Those tools also look at the heating, ventilation and air conditioning systems that complement the building fabric in order to provide the temperatures and the humidity we want. And then within those systems, looking at their efficiencies, how many watts of energy are required in a pump to put water around the system, how many watts are required to drive a fan so that air can be delivered. And then looking at effective air distribution systems and water distribution systems so that we can have the most efficient systems we can find. And through that, we can look at the whole building energy cost across the whole year. And we can look at the amount of carbons that come from that, looking at different fuel sources. So the three steps to say is that first of all, look at the building envelope itself. The second one will be to look at energy efficient measures in terms of the engineering systems, and then finally look at renewables. And when we look at the building envelope, we need to work very carefully to ensure that the building has the optimum shape and size and orientation. So we do need to understand its function, and then the form of the building must follow that. We've got the tools, as I said before, to enable us to study that. We can look at things like lighting, natural lighting and day lighting, introducing skylights and light shelves so that light comes in more effectively into the building, not having to shut blinds during daytime to keep glare out. We want that light to come in and be useful, so we need to design to make that happen. And we can look at how orientation can affect our air conditioning loads. We need to position shading properly so that it does effectively keep the building cool, reduces the amount of solar gains, but it still allows diffuse daylighting to come in. And that can be done with metal systems, or it can be done with natural trees and growth, as we've shown in this slide here. And we can have any manner of solutions to this, as you can see from this slide. It's a matter of engineers and architects working closely together to come up with a solution that it works effectively, but still meets the architectural aesthetic of the building. And we are in a situation here where, of course, the energy consumption over a full 12-month period, of course, is driving to some degree the architectural appearance of these buildings. You can see here the building on the left is highly glazed, but it has fairly big shading systems to ensure that those windows are not overheating in summer. The shade in the middle there shows much smaller windows with much more localized shading systems. And then the one on the right is a curved building, so those shading systems are positioned in such a way that they protect those windows as the sun moves across. We need to look at areas such as roofs, very important. They can be a large area across a building, so we need to put a lot of effort into making sure the roof is efficient. We can use roofs as upside down roofs as access and aesthetic areas, so they part of the asset value of the building, but they are in turn also insulating the areas below that people will be using and reducing the energy consumption. And we can look at more complex solutions such as double skin facades. This is really where we have a two-wall external building, and that gives us a number of interesting options. It gives us extra protection, of course, so it allows us to perhaps use natural ventilation through that with the preheated air in winter and pre-cooled in summer. And of course it allows us to have large windows so we can increase daylight use into the building. And there's a number of successful solutions of that type which we can have a look at and see how they work. And that space that you can see on the left there can be a buffer space where air drawn through that space picks up heat loss from the building, and that air is then drawn into air handling plant and then recirculated so that heat is recovered and reduces the energy demand on the building. And moving on from the fabric, we can also look at how the engineering systems function, and there's quite a lot of opportunity there to reduce energy consumption. But we do need to come up with a comprehensive strategy at the beginning. We need to understand what are our loads in the building and how do they vary throughout the day and indeed throughout the year. So a better understanding of demand profiles is important. And then we need to really develop something which I'd call our basis of design, so that we understand, what direction we're moving in. We need to establish goals for energy consumption targets. And I'd say we need to properly size systems. Oversizing, which was a bit of a habit in the past, is a bad thing to do. It results in inefficient systems as well as the waste of money, of course. I'd encourage us to use good design data, CIBSE guides in the UK, ASHRAE guides, of course. Not really using rules of thumb as design data. Rules of thumb are there as a check, as a back check, to make sure we're in the right area. They're not a method of sizing plants. So the old idea that we size heating systems on 100 watts a square metre or 50 watts a square metre, that's not the way to do it. If we're going for net zero energy, we really have to understand how the building functions, how much heating it actually wants. And for a modern building built to the sort of standards I'm talking about, it will not be 100 watts a square metre. In fact, you might even get to the point of asking whether you need a heating system at all. So we will see much lower heating loads with well-insulated buildings, and we might see an opportunity to heat those buildings with recovered heat rather than boiler plant. And I think we push into that area where we make better use of computerized tools and a fairly good user interfaces these days. They're no longer those complex systems that we had to deal with in the past. And of course, we can double check against other similar building types and get confidence, if you like, in the way we might move with our design by understanding how other people have achieved low energy consumption. I think one of the points I would make, of course, is that we're looking at part load performance most of the time. In the UK here, we design heating systems for the coldest day of the year, which might be today, I suppose. But it only occurs for 1 or 2 days a year by definition. It's the design day. Most days, we have a 240-day heating season, so 220 of those days, the temperature is more likely to be between 5 and 15 degrees C. And that's what happens most of the time. So we need to think about part load operation as well as peak load. And we need to have these variable systems in place so that we can reduce the amount of water flowing, the amount of air flowing around a building, and save energy, because we just don't need that quantity all the time. And as you can show in this slide, we really have to think about that across all of our plant: air conditioning, heating, cooling, pumping systems. And also think about resetting temperature levels. So in the winter, it might be perfectly adequate to come into a building at 20, 21 degrees C and feel warm, and that's good. When you're moving in summer, that building could be at 24 or 25 and feel comfortably cool. So we don't need to have the same set point all the time. So you need to understand how to make that happen. Looking at heating and ventilation and air conditioning, I guess one of the starting points for many of us is, can we use natural ventilation instead of a ventilation and air conditioning system? If we can't use it in the summer, perhaps because the temperature is too hot, can we use it part of the year in the winter? So we completed a building in Chicago which is naturally ventilated for 9 months, and then it has a hybrid ventilation system which comes in and supports the natural ventilation through the 3 months of hot and humid weather. As a result of doing that, we have a building which is using 50% of the energy consumption of comparable buildings in the States. So it's quite a big advantage. So again, it's trying to think across the whole year rather than just trying to design for peaks. And if we're going to use natural ventilation, we need to understand how to deal with diurnal swing. How does the temperature over a 24-hour period change? So if we have a sinusoidal swing, so that we have a hot day in the summer, but in the evening and the night time that temperature drops, we've got a chance for the building to recover. We can use that cool nighttime air for night cooling. We need to think about shading very carefully. We think about how to control window openings. Natural ventilation may want opening windows. It might bring the air in through some other mechanism, but if we are using windows, we don't want them open all the time, because we may end up losing more heat than we gain through an opening window situation. And there are issues such as ambient noise and pollution to think about, and that will affect where we might have the openings. And in some cases, it may be necessary to avoid natural ventilation altogether, of course. Ground coupling is important, so things like ground tubes that will allow us to bring the air in through pipes in the ground or through natural ground spaces will allow us to pre-cool the air in summer and preheat it in winter. And thermal mass is important as well. So the building itself is able to act as a thermal store. In the winter, it absorbs heat, keeps itself warm overnight. The building is still warm the following day. And in summer, will allow itself to cool down all night. So that night cooling, enables the building to operate during the day satisfactorily. Moving to systems in the building which use energy, of course, lighting is very important. So we need to think about how our lighting design works, what is our concept, make sure that we have proper visual acuity and performance, avoid reflections, think about distribution and spread, make sure that we meet the glare indices so that lighting is acceptable, and of course the whole aesthetic appearance. How does light present the space to us? Is it functional and pleasant? People are happy with it. And how that might knit in with natural systems, so that if we have artificial lighting and a natural system, can they work together? Can that one phase through to another as natural light comes up? The artificial lighting dims down and perhaps goes off. And that would lead us into integrated lighting control systems with dimming fixtures, daylight sensors, and even mood lighting. So on the heating side, we've really got to think about heating very carefully. And what I have found with higher levels of insulation in buildings, the hot water loads are becoming fairly dominant, certainly in accommodation, residential, hotels, and those sort of buildings. Offices, of course, hot water is still not a particularly big load, but we may find that hot water in many buildings is a bigger heating load than heating itself. And there's various ways of looking at that, whether we have heat pumps to provide the heating and hot water for us, whether we integrate it with solar hot water heating, and whether we get waste heat from things like combined heat and power systems or heat recovery chillers. When we're looking at ventilation systems, we really need to have a look very carefully at how we might recover heat and cooling. In the summer, of course, that heat goes out. The heat coming in the building can be cooled by the cooled air conditioned air going out, so we're able to recover energy there. And in the winter, of course, the other way around, we want to pick up waste heat that's going out so that we're preheating the air before we get to our heater battery. And that can reduce energy loads and demand significantly. And of course, better introduction of heat recovery chillers and even free cooling chillers. Free cooling chillers are where we would run the cooling chilled water system through the chiller itself and through the cooling towers, but we might not operate the refrigeration system, and we might be able to operate on chilled water that's allowed to float up to higher temperatures, maybe 10, 11, 12 degrees C, instead of trying to operate at 6 degrees C all the time. And that would have a significant energy benefit. And the point about those systems, of course, is that that plant is there and able to run when we do get to our peak cooling days and we do need chilled water at 6 degrees C. It's really just a situation where we're able to drop back and use free cooling when we can. And we can look at more efficient air distribution systems. Underfloor air distribution is one, using the zone underneath a raised floor, which brings air in, and that goes up through the sort of diffusers I've shown here, through a floor box, and that allows air to stack up through the space, passing through the occupied zone, removing concentrations, removing heat from office spaces, and taking that away where it can either be rejected or recovered if it's useful. So underfloor air distribution systems are a fairly new idea, but they have been applied in quite a few buildings in the UK and the United States. And in fact, ASHRAE is rewriting its underfloor air distribution guide at this point in time. They have been quite successful, though there have been issues to do with air leakage in the plenums, and that's one of the points that ASHRAE is dealing with in the guide revision. Those kind of issues have been to do with how well sealed the plenum is, and interesting aspects. For example, controls cabling might go through the floor zone along with all the other cables and data and so forth, but it might then go up a conduit to a thermostat on a wall in the occupied space. And by doing that, it then provides a path for air from the plenum up across the thermostat. So the thermostat is essentially reading the air supply temperature rather than the temperature in the occupied room. and so it's given a misconception of what the room space is, and that's been an issue. So to deal with that, of course, we need to ensure that the conduits are blocked, so we haven't got airflow or air leakage from the space up, and we are actually measuring the actual room temperature. One advance on underfloor air distribution has been the introduction of VAV boxes in the floor. This allows VAV control more locally, and it allows some rooms to be used as seminar rooms or meeting rooms, other rooms as open space office. There's a lot of flexibility there. I suppose just as a final point on that, I was quite interested in the presentation I did at ASHRAE on underfloor air distribution to speak to one of the other speakers from Dallas who completed a scheme, and he told me that his air volumes used in underfloor air distribution in Dallas, which is a pretty hot city, were in fact only 6 air changes an hour, as opposed to on a normal VAV or constant volume system or fan coil system, probably around 12 air changes an hour. So reducing the amount of air we need significantly, because the air on an underfloor air distribution system, really displacement ventilation comes through, treats the occupied zone, and then is pulled out. There's less mixing than with those other systems. Another approach that's been very effective in Europe and is now seeing a lot of use in the United States is chilled beams, and this is where we bring cooling water in, chill air at the top of a room, and that air is cooled and drops back into the occupied space. But the significant thing here is that the chilled water we're using is up at about 14 to 15 degrees C, above the dew point temperature, obviously. And that allows us to run cooling systems at a higher temperature, where we have more efficient operation of the plant, better COPs on our heat pumps and so forth. So a couple of shots of different systems there. We have active chill beams and passive chill beams. Speaking of passive, of course, that brings me on to the whole idea of, if you like, surrogate thermal mass through the use of phase change material. And this is material which, in this diagram, I've indicated as plus ice cells, and these are containers which contain a material which is solid within the plastic container, but it changes into a liquid as it absorbs heat at a constant temperature. It's obviously a latent heat because it's changing from solid to liquid, and as it does that, it provides a cooling effect to the room. So warm air rising from the desk during the day there is cooled and drops back down to keep the space under control, and then during the night air is brought in to refreeze those cells. When I say refreeze, this material is selected to freeze at a temperature we choose, typically in that application at about 24 to 25 degrees C, so the space below is maintained at about 21 to 22 degrees C. So here's an example of a project where I used it in Burnley. It's Pendle Vale College. This incidentally was the first A-rated EPC school in the country, and the pictures here show a classroom in the centre, and the picture on the top left-hand corner is looking into the ceiling void, and you can see these white plastic tubes which are mounted on a frame there above the ceiling, and you get another shot on the right-hand side. And the bottom low-hand corner looking into the ceiling void, you can see the open grid ceiling tiles there which allow the air through. They're not all open grid actually, but about half of them are, and that allows the air through into that space so that the air is cooled and drops back down into the classroom below. And I did this on a 30 pupil classroom and also a 120 pupil seminar room, and it works fine. We managed to avoid air conditioning in both those spaces. We maintain temperature, and it's basically, if you like, free air conditioning. Moving perhaps into a more bigger picture is to look at district energy and how that works. And you can see that if we look at district energy plants, we can now start serving a whole series of buildings with low carbon and even zero carbon energy, depending on what our energy source is. I still think that gas is probably our best option. It's relatively cheap and plentiful, although it is going up in price. But it's not, of course, carbon neutral. It's low carbon. But we can look to use biofuels and waste recovery plants and so forth. And there's methods of doing that. We will get good efficiencies, better than a power plant, probably 70% or more. And of course, we can ensure that we can use that all-round heat that's available from these systems by looking at absorption chilling in the summer. So we take that heat and use it to cool buildings. And then, of course, once we've done that, we can look at the renewable energy systems, which would complement our building. And just go through these fairly quickly, be familiar with them, but solar water heating systems using panels to take the sun's energy and convert that to hot water, which can be used for either heating or hot water consumption. And we can look at photovoltaic systems, which we would generally put on the roof of a building, and we can use that to generate power. And we can either use that in our building or export it. And I think really in the UK environment, if we're not looking to air conditioning summer, we're probably going to generate a lot of PV power at the summer. We don't really need it, so we export it back into the grid. But of course that makes up for the energy that we have to draw from the grid and from the gas supply during the winter, and that's really how we effectively get a 12-month zero carbon building, zero energy building, although we have had to use energy in the winter, of course. And there's different ways we can use PVs. We can use them in glazing systems or panels or tiles and so forth. Interesting thing just to consider here, and this is a slide from Drew Crawley in the United States when he's with the Department of Energy, and it looks at the effects of the height of a building. So clearly, if we've got a low plan building, 1 or 2 floors, we've got quite a lot of roof compared to the area of floor, and we might be able to get away with covering that roof with PVs and getting a low energy consumption. But as we start to go up in size, thinking of buildings that are maybe 10 floors high or more, the area of roof space relative to floor space is much lower, so we're unlikely to really have a massive impact. So PVs is a good answer for low rise. High rise is probably not the right solution. The right solution might be something like geothermal, and this slide illustrates the different solutions. We have an extraction well, where we have ground loops, pond loops, or energy piles under the building. Now moving into where our targets might lie, our particular target in the UK is to have zero carbon schools by 2016, and that comes from this carbon task report by government. And we went some way to meeting that on schools in Burnley using thermal energy storage systems. We recognised that we were doing cooling in parts of the building, the IT room, the data room, and we thought we would bring that heat back, store it overnight, and then we could use that the following day for heating the building up. And what was fairly interesting in these highly insulated buildings is that we did want heat about 7 o'clock in the morning, but by 8 o'clock the buildings were warm enough due to the gains from people and occupants and lighting and equipment in the building. So the heating wasn't a continuous requirement through the occupied period, it was really just a preheat requirement. So thermal storage seems to give us a solution there. Other renewable energy sources would be wind systems. They really require us to ensure that we have the amount of wind around at the right time. Biomass has been useful, looking at how we might use timber or waste or other products to generate power. And then finally, I just want to touch on zero energy systems, because there's cities where we look to have plant pick up that waste heat that we currently throw away from our power stations, but to use that to do heating within the buildings and of course cooling in summer. And there's big advantages to that. One place where we have done that successfully is Media City, which has a tri-generation system, and this illustrates the pipes as they were going into the ground, and up on the left-hand corner, a sort of an architect's impression of Media City. And that is now complete. This is a distribution of pipework underground. And just touching on the environmental benefits there, that was one of the major reasons that this site was awarded the BREEAM Communities Excellent Award. We were able, through this system, to use the canal water for free cooling. It rejected heat when we didn't want it, but more importantly, in summer, we're able to use free cooling from the canal, and was calculated to be worth about £300,000 to £400,000 a year by just using, to say, canal water. And that's led us on to other waterside developments, looking at how we can generate wealth, if you like, through a low carbon approach to life. And I guess moving on fairly quickly here because I want to allow time for questions. It leads us to look at that holistic approach. How can we make sure that low carbon agenda just generate wealth, generates jobs, and that's something we're looking at in those Liverpool projects, where Liverpool Waters and Wirral Waters, where the buildings will be low to zero carbon, and as part of that, we need the industry to deliver that. We need products, and we need people who can operate those kind of buildings, and that's really where the low carbon UTC that I mentioned really comes in to bring young people into the industry. And then we might look at how we look at these cities in terms not just of their energy, but the economic benefits, what kind of jobs will be created, and how can we use that to cut fuel poverty, create employment, and so forth. So zero energy cities will be looking at a more self-sufficient level. They'll be using waste as a resource rather than a waste product. We'll be talking district energy, of course, and using surplus energy from one building to feed another. We're going to use that mix a lot more. We will be needing to look at thermal storage so that when we do have energy, we don't throw it away, we hold on to it and use it when the time comes. And that will require us to get a better understanding of energy profiles. It will also allow us to energy back into existing buildings and help us to regenerate those as zero carbon buildings. And then finally, I just want to touch on a couple of examples. These are from the United States. I'm going to go fairly quickly, but they're all relatively small buildings. This is the Aldo Leopold Foundation in Wisconsin, which is a zero carbon building, predominantly using PV panels. Again, following that approach I described there with natural ventilation, energy efficient engineering systems, and good building fabric. This is the Environmental Technology Center in California. Again, only 200 square meters. It's a relatively small building, zero energy rated, but in this case using PV panels as a renewable input to supplement the grid use. A fairly unusual building here in Hawaii, and a massive structure, as you can see, holding an array of PV panels, which make that building a zero carbon building. It's the visitor center to their energy center in Hawaii. And then this environmental studies center in the United States, slightly bigger than the others at 1,260 square meters. It's a two-story building, but you can see again from that diagram a fairly hefty PV array, and they've also used the adjacent car park roofing to hold PVs. I just wanted to touch on, to finish, I'm looking at a 1960 church here in Leyland where I live, and we are looking to, well, we installed PV panels, as you can see there, on the roof of that building, which is the clergy building next to the church. And that's going to generate zero carbon energy, which we will use to drive a heat pump, which will take heat out of the adjacent lake. And that heat goes into a thermal store, and then will be used to heat the church up. So we're looking at a zero carbon heating system there. That's moving ahead at the moment. It'll take about a year or so to complete. But I think it's an interesting one because it's a listed building where we can't upgrade the fabric. We just aren't allowed to touch it. But we've gone the other way and looked at the engineering systems and how we can use, if you like, natural ambient energy and using a PV energy source to make sure that we are able to convert that. So that's a fairly quick run through of what is effectively a half-day course. I've taken out a lot of slides out, obviously, and if anyone ever wants to go on that course, please let me know. But I'd like to stop there and ask if there's any questions.
Okay, Frank, that was fantastic. Thank you. Tremendous amount of information there. I can see you've crammed in your half-day course there, so thank you very much for that real scamper through an amazingly interesting subject. We have had lots of questions coming in, Frank, which shows you how interesting people find this topic. And the first thing, it occurred to me straight away, because it's very topical, and to a number of our people online, was the issue of the US in particular pushing for energy independence by exploiting new supplies of fossil fuels, particularly shale gas, And one of our, that was something I wondered if that alarmed you in this context. Also, one of our attendees has suggested it makes the whole concept of zero energy buildings more difficult to sell to clients, because he's suggesting that if energy is going to get more affordable and more available, it's more difficult to sell that concept. What do you think of that?
Well, that's true, but I think the approach which ASHRAE is taking is to push down that road towards zero carbon as soon as possible. We obviously still need fossil fuel energy, but the longer we can conserve what we've got, the better, really. So I think these shale gas finds are good in the sense that they give us better independence as countries, but it doesn't mean we have to use them up fast. I think we've kind of learned from past practice, such as North Sea gas, is like it's a great find. Let's still do the right thing and be efficient and conserve that as long as possible. It seems incredible to me that we've really got through North Sea gas. You know, we've got 2 years worth left here in the UK. We got through it, you know, not within a lifetime, but in part of a lifetime. So the lesson is. Yeah, fossil fuel's great. Let's just not use them up so fast. And I think the Americans have got that message. But you know, even if they didn't, if they thought, well, great, we've got cheap fuel, let's use it. I mean, of all the countries in the world, you know, apart from these islands in the Pacific, they seem to have the lowest cities, as far as I can see. Miami at 1 meter above sea level. You know, that's not going to hold that sea back. You know, even Mr. Obama can't do that. So they're going to have to take some action. Otherwise, they're going to lose a lot of valuable real estate. And there's no reversing that, of course, once that happens. So yeah, it's good to find more fossil fuel, but let's just make it last longer and do the right design and engineering approach for our buildings as we move forward.
Okay, yeah, Frank, that's a very good answer. Very good point. Yeah, yeah, good to have shale gas, but let's not waste it like we waste all this other energy. We got a question from Patrick Catton in Beirut. So hello to our friends in Lebanon. He was just asking a specific question about the energy use figures you use for US buildings. Do those figures refer to buildings in general or specifically to commercial buildings?
Those figures were commercial buildings. They were provided by Department of Energy. I think Drew Crawley and others who are on ASHRAE, and that data's available in some of the ASHRAE handbooks. Those are updated, of course, regularly, but that's where I got that information from.
Okay, no, that's great. So it's okay, that's fine. I hope that answers your point, Patrick. A bit closer to home, we've got Kate Fry in Exeter. Kate was asking about PV. She's saying, if electricity is such a small percentage of building use, why is PV so popular? And why does PV have such a large effect on emissions, considering the poor energy production of PV? And it gets highly rated on EPCs, energy performance certificates. What's your feeling on PV, Frank?
Well, PV as an option, it's a renewable energy option, of course. We've only got a number of them that we can choose, but it is a relatively simple one to put on a building. The technology has developed to the point now where we can just come to apply it to a roof or sometimes a wall, but more often a roof. And then once it's on, it just generates electricity. But I think, Kate, we're playing a numbers game here in a way. We might not want to use all that electricity, but what we do is we use what we can, we export the rest, and then we add the numbers up and say, actually, that made up for the fact that I bought all that gas in the winter, or I got electricity from the grid, you know, during the winter. So over the course of 365 days, the amount of energy generated by a PV system, whether I've used it in the building or not, is more than I used in the building. And that's essentially what we're demonstrating. We're not trying, well, you could, of course, and I did do a building where we did this. We're not trying to make a building autonomous. We still connect to the grid, but what we're trying to do is put enough power back into the grid and to make our building efficient to a level where we can say that over a 12-month period, we're zero, or we're negative carbon. I mean, I think if anyone is familiar with BREEAM and you know how that works, you've got to be better than building regs. So clearly, in 2016 onwards, you're only going to get credit if you go negative carbon. Sorry, it's a bit of a long-winded answer there, but PV is an option. It's a simple one. It connects in fairly easily. The other ones like wind, you really have to have the wind profile to make that work. Biomass, again, if you start using biomass, you've got to have the thermal storage systems that go with that, so you can generate the heat and then store it and pull it out as and when you want it through a fluctuating load profile. So PVs are a good solution, I think, but you've got to have the roof area as a demonstrator. If you're putting up the shard or something like that, you just haven't got the roof area, so there's practical issues. Okay.
Okay. Good. Yeah. Thanks, Frank. Okay. Good point. Good point. I think hopefully that's answered that question, Kate. A number of people are troubled about this heavy focus on new buildings, new design, when in actual fact the big energy problem is in existing buildings. Few asking, should we be more focused on the work to do with making existing buildings more energy efficient, Frank? Georgiou in Cyprus, so hello Cyprus. I'm thinking they sound like the Eurovision Song Contest here, sorry. Hi George. George is asking specifically about which thermal comfort model you would recommend for existing residential buildings to help reduce energy use in those. So just a general point about existing buildings, Frank.
Yes. Well, I mean, on the general point, I think you're absolutely right. They are the majority of the buildings that we've got, and they're going to be around for a long time. It's very hard to go in and improve them thermally. I mean, we can do a certain amount, but we can't really get them up to, say a passive house standard where they don't need any heating. They're going to need some, but I see the easy answer there to start sharing energy between buildings. So a district energy scheme allows you to do that. In this country, we generate power and throw all the heat away. So we've got big source of heat there that we can tap into. But even a thing like a data center, when we put data centers up, we tend to go to great pains to take the heat away and throw it away. Why not have a data center feeding heat into another building? And I know the reason we don't do that is because the data center operator doesn't want to be a heat seller. He wants to be a data center operator. But there's big opportunities for heat recovery there, and using that, if you like, that unregulated energy, because Part L is talking about regulated energy, not unregulated, but trying to use wasteful heat sources to heat these big old buildings up, and we then don't have to go down the road of trying to insulate them. In terms of the comfort standards, I think CIBSE has good comfort standards there, which do allow that shift. But I think the ASHRAE standard 55 is probably the best one to follow, because it's the adaptive comfort model. It does allow you to work through different climates during the year. So ASHRAE standard 55 I'd look at. Okay.
Thanks, Frank. That's great. Talking about different climates, we have Adrian Ayora was saying, could you mention, I think you did talk a bit about at the beginning about the fact that you're trying to achieve this in different climate zones. And Adrian's particularly asking about, could you touch on tropical climates where there is reduced temperature variation throughout the year? Does that pose particular challenges?
Well, I think it will do. Well, we're looking at issues in Africa, and there is an abundance of solar energy there, so you can start generating more power through PV than we can, for example. So I haven't really done a lot of work there myself, and this picture of me at the back here is in Calgary, where I went to the cold climate conference. And this seems to be a bigger issue in these cold climate areas where they have very short winter days. The temperatures are down at -20. In fact, one of the presentations on the Yukon, the temperature was -50. So they've got big thermal energy demands there for prolonged periods, but without having access to solar gains and so forth. So that seems to be more of an issue in a way. But yes, I think we can produce zero carbon buildings in the tropics fairly easily. But we've got to make better use of solar, PV and that kind of thing. That cold climate design guide that I mentioned, that committee has just been set up. If anyone wants to get involved in that and they contact me, I'll put them onto the corresponding member list, and it will be a guide which we published in 2014. But within there, I want to cover solutions for net zero energy buildings in cold climates. Okay.
Okay, thanks, Frank. This sort of the questions are coming in thick and fast, and we're just about out of time. So I apologise in advance to anybody who doesn't get included. I'm just going to grab a few here. Salton in London, he's seen instances where SBEM modelling assumes that air source heat pumps are more, I'm assuming, more energy efficient than ground source heat pumps. Is that actually true in practice, in your experience, Frank?
Well, it depends where you use them, doesn't it? I mean, this is a point that came up in Calgary. I mean, clearly an air source heat pump in that kind of climate would have a COP of probably 1 or less, and at -10 probably wouldn't work at all. So yeah, it's a good point, Sultan. I think you've really got to know where you are with these things, and then look at the COPs over the season. Maybe put it in and you switch it off when it gets very cold and switch to a gas boiler or something. But yeah, excellent point to raise.
Yeah, it's good thing.
You really have to know where you are.
We're getting close to our cut-off time, but there's quite a large point, which I think is a nice way to finish, is looking to the future beyond what you're talking about now, Frank. Matt Jack Kasperick in Bristol saying after 2019, when all new buildings will be zero carbon. Well, that kind of depends on whether we hit Partel targets, I guess, doesn't it? But possibly in theory. I say, are we going to stop at zero carbon development? Magic wants to ask, or will buildings eventually become negative carbon, producing clean energy and easing power plants? Cast your predictions forward a bit here, Frank.
Yeah, we're going to go negative, aren't we? We're going to have negative carbon. I think that will drive that will be the BREEAM credit for energy. So if you look at BREEAM, you'll only get extra credits if you go negative. So that's where the A+ comes in on the EPC as well. Of course, that's looking because an A-rated EPC is zero carbon. A+ I think is negative. But yeah, I mean that's all. At the moment, we're all worrying or struggling how to come up with zero carbon. But you're right, we're going to be driving on beyond that. And buildings can contribute to the grid. Yes.